After watching this video, you should understand the following. You should be able to understand Coulomb's law and how to apply it. You understand the vector nature of electric force. You understand the concept of the electric field and how to quantify that. And finally, you understand how the electric field is applied to point charges, dipoles, and parallel plate capacitors. We know from Newton's third law that objects exert an equal and opposite force on each other. And we've learned that the forces for charges are either attractive or repulsive. We are now going to look at how we can put numbers into this and quantify this electric force. The scientific principle that governs electric force is known as Coulomb's law. In Coulomb's law, we can talk about the force of one object on a second, and because of Newton's third law, we know that the force of the second on the first is the same, and sometimes you'll see me write it as just F sub 1 comma 2. Here we see the equation that comes from Coulomb's law, and we will talk about it more in depth in just a minute. But I'd like for you to look at how similar this equation is for the electric force to the equation you learned earlier for the gravitational force. The similarities and differences between these two forces will become evident as we continue in this chapter. According to Coulomb's law, electric charges exert an electric force on each other. And here's the equation for Coulomb's law. Let's look at all the parts for this equation. On the right-hand side at the top, we have Q sub 1 and Q sub 2. These are just the two electric charges. Notice they are in absolute value because we are not using their signs. We do not care if they are positive or negative as we are completing this equation. On the bottom, we have the distance squared. I know it says r, but it's the distance. It's not a radius. Finally, up on top we have this capital K. This is a constant, and it is equal to 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. Sometimes you might see that as 8.99 times 10 to the 9th. This equation gives us the electric force. From the equation, we can see that the electric force is directly related to the magnitude of the charges. And let's look at a few examples to illustrate this. First, if I double one of the charges, then that will cause the electric force to double. If I double two forces, then that will cause the electric force to quadruple. Likewise, if I cut one of the forces in half, the electric force will be cut in half, and if I cut them both in half, the electric force will be cut in 1/4. We can also see that the electric force is inversely related to the square of the distance. What does this mean? Well, if I were to double the distance between the two, well, 2 squared is 4, and the inverse of 4 is 1/4, so the electric force would be cut by 1/4. However, if I were to cut the distance in half, 1/2 squared is 1/4, and the inverse of that is 4, the electric force would be multiplied by 4. It's important to remember that electric forces are just like any other forces. For example, they can be added together. And that's the same whether you're adding two vectors, or if one is in the opposite direction, you actually end up subtracting two vectors. You might not like seeing this, but electric forces are just like other forces in that they are vectors. In other words, if I have a force that is being directed at a certain angle theta, then I can find the horizontal and vertical components of the force by using trigonometry. Likewise, I can add a horizontal and a vertical force together by using the Pythagorean theorem and inverse tangent. Let's look at an example of how the electric force is calculated. Now I want to find the force of charge 1 on charge 2. So let's imagine that charge 1 is nailed down so that it can't move. And I'm going to show that, I'm not going to leave the nail there, I'm going to show that as an X in the circle. And I want to find what the force that charge 1 exerts on charge 2. So I'm going to use the equation from Coulomb's law that the force is equal to K Q1 Q2 over R squared. And in this equation we know the following values. First, we know that K is equal to 9.0 times 10 to the 9th. We know the two charges are equal to 4.0 times 10 to the negative ninth coulombs. That's what the N means. Nanocoulomb is times 10 to the negative 9. And the other charge is negative 2.0 times 10 to the negative 9 coulombs, but we're only going to use the absolute value of that. And finally, we know that the distance between the two is 0.05 meters. You need to change centimeters into meters. 0.05 meters squared. And when we put all of that into the equation, we get the following answer. So the force of charge 1 on charge 2 is 28.8 newtons. And because I can look at the signs and see that one is positive and one is negative, I can give you the direction of the force vector as moving towards the left, since it would be an attractive force. Now let's see what happens if we move the distance in to where it's only half the distance. Well, I know that because of the inverse squared relationship, 1/2 squared is 1/4, and the inverse of 1/4 is 4. So therefore I would multiply my previous force by 4, and I would get 115 newtons. And this concludes this video.